Hello everyone! We are going to present the paper entitled Smart Drilling for Aerospace Industry, a State of Art in Research and Education. My name is Ana Carla Araujo and I'm presenting with Landon. We wrote this paper with Pierre Lagarrigue. We are part of the Institut Clément-Ader in Toulouse, France, and our group in research for machining is called Radical. For the agenda today, we are going to talk about the motivation in drilling process for aerospace industry, especially materials, machinability and heterogeneity, the combination with machine tool dynamics and cutting parameters that together compound the industrial Internet of Things applied to drilling strategies. We are going also to present some examples in smart drilling and briefly a connection between smart drilling innovation and teaching in Toulouse. In aerospace industry, workpieces are getting lighter and lighter. The laws and directives are pushing hard for the reduction of carbon emissions, and the workpieces nowadays are mainly composites, 50% of the new airplanes, and metallic material, mainly aluminum alloy, nickel alloy, titanium alloy, and stainless steel. All those materials has very low machinability and different cutting parameters. Talking specifically about drilling, there are thousands of holes that needs optimization. Especially now with the worldwide crisis, it's very important to optimize, and we are using smart manufacturing for identification of material and optimizing the cutting parameters.
The axial drilling process is widely used in the aeronautical industry, especially for making fastening holes with high requirements in terms of hole quality and surface integrity. Drilling multi-material stacks is common, but it remains a challenge since it has to be performed with the same tool and in the same cutting conditions. If we consider the recommended cutting condition in each material for a given tool, for example given by a tool material pair methodology, it can be really difficult to define the optimal cutting condition set for drilling a multi-material stack. As an example, drilling a titanium, CFRP, aluminum stack is really a challenge with a cutting speed that will be imposed by the titanium layer concerning the tool life, and the feed that will be limited by the CFRP laminate because of the delamination problems. Like this, the set of cutting conditions will not be optimal for any material. For a CFRP aluminum stack, it seems easier, but necessarily the feed will be limited as well. You can see in this example the thrust force and the torque obtained in this configuration. Smart drilling seems so to be possible, defining cutting condition set different for each material. But these problems of cutting conditions is not the only issue. Indeed, different problems may occur during multi-material drilling, like diameter ovalization, flaking or delamination of composite laminate, burrs, and so on. It is thus necessary to control the process in terms of cost, of quality, of course, to achieve, for example, one-way assembly, but also to ensure in-service strength of the assembly, and also to control the reliability of the operation, which is the main problem due to the evacuation of the long chips. Different innovative drilling processes have been developed to solve these problems. We will focus in this presentation on two of them, since they are used in industry. The first one here is vibration-assisted drilling developed by Metis. For this process, a low-frequency forced oscillation is added to the feed motion of the tool in order to ensure the fragmentation of the chips. A large amount of work has been done on this process, especially in our lab, modeling the tool trajectory, the bottom contact, simulating the chip removal, and the force signals. You can see here an example of force signal in aluminum, but also in a configuration of drilling an aluminum CIRP stack. If the thrust force is quite the same as both materials, the torque is clearly different. Smart drilling strategies can be developed for in-process cutting condition modification in real time and to use cutting conditions that are optimal for each material. The second innovative drilling process that is used is orbital drilling, also called helical milling. In this process, the tool diameter is smaller than the hole diameter. So the hole is machined with the cutting tool following an helical trajectory into the material. With this process, we can see here an example of force signals during a titanium alloy. In pink, the axial force is the main one, but also in green and red, we have the radial forces that are really significant also and important to control to limit the tool bending that can occur. With this process, the burr height and delamination or fracking of composite laminates can be limited. But we can encounter another problem, which is the formation of a cap at the exit of the hole. So this process has to be controlled, and a large amount of work has been done in our lab with this process to simulate it, to model the forces, or also to control the fatigue life of the drilled structures. Moreover, considering an example of CIRP titanium stack, we show in this slide the force signals and the current signals from the rotation and feed motors. As for other drilling processes, the transition between the materials can be detected quite easily, and we developed smart drilling strategies based on these signals that permit to define a set of cutting conditions for each layer, that is, each material, but also another set of cutting conditions for the transition in order to recognize the material, limiting like this the current variation. So, finally, we can see that smart drilling strategies can be developed for multi-material stack drilling, but some issues have to be overcome, like fast detection, especially with the presence of a titanium layer, but also signal processing, cutting condition modification in a short time, tool wear consideration, and so on. Anyway, monitoring the process is really a key point.
For smart machining, we can use several sensors for online monitoring. We can use the data from the dynamometer, as it was said, forces and torque. We can use temperature, acoustic emission, and several other sensors. But especially in this case, we are using the machine tool data, especially the power consumption. The power consumption is one of the signals that the machine uses for its own working process. In our decision-making process, we are going to use the spindle current, the spindle speed, axis position, and power consumption in the CNC data. We can see in the work from Lee et al. In 2016 that it was compared several machines and the total power consumption from several parts of the machines. And we can see that the machining part is always constant. So we can use that part for our decision making. In our case, we make an example in the lab and we compared the data from the CNC Profibus and the wattimeter, and we used also the data acquired online from the machine as torque, current, and spindle speed. So each point was taken in one control loop in the CNC. So if we take the signal trace from the CNC machine, we can identify the materials. So in the left, there is the active power from the spindle of the machine, and we can identify the accelerating spindle, the peak in the left, and followed by the cutting power that can be identified in the middle. So we can analyze only the cutting part. We compare this signal with the signal from the wattimeter, and as we can see, both are similar, both are superposed. The blue one from the wattimeter and the red one from the Profibus. So if we take this signal, the cutting power, and we divide by the cutting speed and divide by 2 for each cutting edge, we can calculate the average tangential force per cutting edge. Then we can see the titanium and aluminum differently. So the three materials, aluminum, composite, and titanium, they share different parts of the diagram thrust torque. Then if we can identify from the machine data from force and data from torque, we can recognize each material. A very important point that we want to present is the connection between research and teaching. Even though everything we presented up to now is research only, we need to make a connection with the practical work in engineering school. For example, in the 5th year of engineering school in Toulouse, we are adding a practical work that the students collect CNC data, especially from the position of the tool, and they compare with the trajectory it's being planned by the CNC code. So they can do first a diagnostics on the machine. They will see the gap between the planned trajectory and the real trajectory. And second, they understand that each machine is one thing in the industrial Internet of Things. Another important point is that in Toulouse, we are building a new laboratory that will be shared between different schools of engineering. In this new building, called Maison de la Formation Jacqueline Auriol, is an industry school that we are going to present different subsets, different manufacturing, all connected and all trying to show the new industry, the industry for the future. I would like to thank you very much for your attention, and I would like to invite you to visit our channel, Radical, in YouTube, where we are putting all the experiments we do in the lab and also the simulation. Thank you very much. Have a nice day.